Hi everyone, it's great to have you join us for today's webinar, Evaluate Sensor Cleaning with Confidence Using Multi-Flexible Body Dynamics. In a previous webinar, we covered the use of the moving particle simulation solution ParticleWorks to understand the effect of vehicle soiling and how to reduce sensor blindness. But today, our senior project engineer Danijan will take you through the use of multi-flexible body dynamics to evaluate the efficiency of the cleaning process. But we also have David here to give us a quick recap of ParticleWorks. Would you both like to introduce yourself?
Hi everyone, so my name is Danijan and I'm a senior project engineer at EngineSoft specializing in multi-body dynamics. My key role is supporting clients with functionality evaluation and design development, including rigid body and flexible body analysis. My recent projects involve working with the medical industry and also the autonomous vehicle industry, helping with concept evaluation and device development.
Hello, my name is David Percival and I'm a Senior Project Engineer for EngineSoft UK, and I'm the UK Lead Engineer for all ParticleWorks activities. So I work on consultancy projects, methods development pieces, training and software sales.
Thank you, David. Thank you, Danijan. So just before we get started, just like to remind everybody that you have just been muted for the efficiency of today's webinar, but feel free to use the chat box to ask any questions that you might have throughout. We'll endeavour to cover as many questions as we can in the Q&A section at the end of today's webinar. But let's get started. Over to you, David.
So before Danijan gets started, taking us through this interesting case study, I wanted to give a little bit of a background and explain what ParticleWorks is and what is the methodology behind it and why it's so efficient for this type of simulation. So the engine behind ParticleWorks is a methodology called the Moving Particle Simulation Methodology, or MPS. And this is a smarter approach to CFD. In very high level overview in terms of what's its main features, well, first of all, it's a meshless methodology. Because of the lack of a mesh, it means that we are well optimized for solving any simulation with a splashing element or any free surface. So there is a water and air interface. And the reason for this I'll come on to in a few slides time, but overall it is much faster and far more accurate than a traditional mesh-based solver. And again, without the necessity of a mesh, moving boundaries are far simpler to deal with. So we don't have to worry about things like mesh overlap, mesh deformation. Overall, it just means that our pre-processing time is far, far lower than a traditional mesh-based CFD. Now, the physics behind the MPS method is exactly the same as traditional CFD. It's still solving the Navier-Stokes equation. However, it's just a question of how we solve those equations. So the MPS method was actually originally proposed by Professor Koshizuka of the University of Tokyo, and he is one of the co-founders of Prometech Software, the company that develops ParticleWorks, back in 1996. Now, ParticleWorks is actually the only tool on the market which uses the MPS method. There are other particle-based CFD tools on the market that use a methodology called Smooth Particle Hydrodynamics, or SPH. However, this methodology was developed for compressible fluids, and is not well suited for simulation of any fluids that are incompressible. ParticleWorks is the only particle-based CFD tool which was designed for simulation of incompressible fluids. So the way that we differ between conventional CFD is how we solve the Navier-Stokes equation. So conventional CFD is solving on the nodes of a fixed mesh. This is like taking the outside point of view of solving the equations, which we could call the Eulerian approach. The MPS method, however, is solving from the point of view of the particles. So we're taking the Lagrangian approach of solving the equations, and this means that the particles kind of act as a moving mesh that moves with the fluid and allows us to resolve the free surface very accurately and in a very efficient manner. The reason this is so efficient is because, well, in the conventional CFD, we are wasting a lot of computational time in regions that we're not interested in. So we can see here that the water is in this blue column on the left-hand side here, but all of these white nodes are just wasted computational time. In the MPS method, we are only solving where the particles actually are, so far more efficient before we even start the simulation. As the simulation then progresses and the free surface evolves and moves, we can see that the only way we can capture that free surface accurately at all time steps is to have a very fine mesh throughout the entire domain, which clearly is going to massively increase the number of nodes and massively increase the computational cost of our simulation. Now, in the MPS method, there's no requirement for a fine mesh everywhere. The particles will act as their own mesh, and it means that we're able to resolve that free surface very accurately, even if we didn't know the fluid was going to go into that region. So you can see in this case, we've hit this far wall and splashed up and out of the box. However, we're still capturing that free surface very accurately, whereas in the conventional method, we may not have realized that the fluid is going to go into this region, so we either haven't meshed in that region at all, or we've simply meshed it very coarsely, which means that we're going to lose information and overall the accuracy of the simulation. So now I just wanted to include a quick testimonial from one of our longest standing clients in the UK. Hewland Engineering are market leading automotive and motorsport transmission manufacturers based here in the UK, and they've been Particle Works users for a number of years now. We will play the video in the webinar, but if you want to watch this on your own devices, please just scan this QR code.
Lubrication has always been of paramount importance within the transmission, and whilst we have the tools to analyse the pressurised system, the splash element has always been a best guess during the design phase. This means that in order to prove our thinking, we had to deploy costly 3D printed clear casings and produce a full set of the components of the design to run on our gimbal rig. The downsides to this is having to produce the 3D casings. They're costly, it's time consuming. We have to have a full set of internal parts produced before we can test. And in motorsport, time is always the biggest challenge. There's always a lot of pressure from the customer. There's always a lot of internal pressure to get the project finished on time, delivered, and right first time. We've always been aware of traditional mesh-based CFD and that it could help us in this situation and give us an upfront look at the problems that may arise. We became aware of particle simulation and started to investigate the tools available, as it seemed like the perfect solution to our problem. So EngineSoft arranged a trial for us. During that time we did some testing, so correlation testing, virtual versus reality if you will, and I have to admit I was surprised by the correlation that we achieved. EngineSoft and Particle Works stood out to us, basically in terms of both the ease of use of the software, the solve time and the support structure surrounding the software. That allows us the ability to deliver a right first time project, meaning that we don't need to have an expensive prototype test rig. Training other members of the team to use it has been very easy. It seems very easy to pick up and be able to run simulations very, very quickly. During the trial period, we saw so much benefit from the software that the transition to a full license became an easy decision. Overall, this method offers us a huge time saving and allows us to do this work up at the front end of the project rather than at the end. Typically, we would go from CAD to test in around 10 to 12 weeks. With Particle Works, we can do that in 3 days. I feel that having this capability gives us an edge over our competitors. There are many other benefits and improvements that we're finding all the time due to the insight given to us by Particle Works. The motorsport industry moves at such a fast pace that it's vitally important that Hewland stay on top of new technologies. Efficiency is becoming more and more critical in transmission design, and having the upfront capability allows us to minimise losses due to churning and run lower oil volumes, resulting in lower overall mass. EngineSoft have been a great partner to have on this journey. Their knowledge and their support have been invaluable to us and second to none.
If you want to learn about how other companies are also using Particle Works, I invite you to go and watch some of the recordings from our first annual Particle Works user meeting, which include presentations from some of these big names in industry. Again, if you want to go and watch these in your own time, then please follow this QR code to watch all of the recordings online for free.
Okay, so in this webinar, we'll be discussing how multiflexible body dynamics will be used to evaluate sensor cleaning. This is a follow-up to a webinar presented by David a few months ago on sensor soiling. So this is a follow-up to it where we discuss the next step, which is sensor cleaning. So for a bit of background, so a lot of vehicles are becoming more and more autonomous. There's new features in vehicles, ADAS systems, such as adaptive cruise control and lane assist. And these systems rely on various sensors dotted around the cars to function and give them information back to be able to act on it. So it's very important to keep these sensors clean at all times, so the vehicle is able to scan the surroundings around it and provide accurate information back to the actuators to provide the correct action. So that's very important to make sure that the perception is accurate, the visibility is good, and the correct action is done. And this is obviously paramount for passenger safety. But obviously keeping the sensors clean required a cleaning system, and these need to be efficient both in terms of fluid use and also use of electric charge. So in terms of fluid, you want to keep the minimum amount of fluid in these vehicles to reduce the overall mass, and also to reduce the number of times you would need to refill the vehicle with these fluids. But also in terms of energy usage, you want this system to use the minimum amount of energy so that most of the energy is used for the actual propulsion. So discussing vehicle soiling. So what is soiling? Well, soiling is the accumulation of dust, dirt, mud, and any other contaminants on the vehicle's surface. In this particular case, we're focusing on the sensors, and obviously this soiling on sensors can affect their ability to accurately perceive the surrounding, and this could, as mentioned, compromise passenger safety. So what are the problems surrounding this, and what we're trying to do? So one of the key things is to reduce the soiling right in the sensors. So this was actually presented by David in terms of how we can provide the correct countermeasures to reduce the soiling rate. But as we know, we can't eliminate soiling entirely. There will always be some sort of dirt or contamination on the sensors. So the next step is thinking about how can we clean their sensors, but also how can we clean them efficiently. So how can we make sure that there's no we're using the minimum amount of energy to clean those sensors, and also making sure that they are cleaned as quickly as possible. So this is just a bit of a highlight reel of the last webinar, sort of describing or simulating the soiling, whether it's self-soiling or soiling from the vehicles and contaminants. And we can see on the bottom right here the sort of occlusion on the sensor itself. So for this webinar, we're looking at the cleaning of these sensors. So it's obviously very important to keep the sensors clean as mentioned, but it's quite difficult to physically test these cleaning systems as we haven't got a vehicle design, we haven't got it manufactured to design the vehicle and the system around it. Can be very expensive, and so it's quite late also in the design process. So it's very important to try and bring this forward to the design phase, so we have some analysis with concept designs. So we've got at least a starting point when we start to create a physical prototype. And then focusing on simulation. structural analysis is quite, it's not very sufficient for some of these cleaning systems, especially in the one that we're going to present, which is based on a wiper blade. It's quite a dynamic system with very large translation and motion and deformation. So it's a very dynamic system, and in this particular case, a static structural analysis is not sufficient. And also, mesh-based CFD is incapable of including the soiled surface that we're going to use in this particular analysis. But also, it's unable to efficiently co-simulate or couple with a dynamic analysis or structural analysis. So what's the solution that we propose? Well, it's to use a multi-body dynamics tool that's able to include flexible bodies and also couple that with a particle-based CFD tool. So in this case, we're using Recordine as our multi-body tool and ParticleWorks as a particle-based CFD tool. ParticleWorks uses the MPS method, which is a mesh-free particle-based modeling methodology. So the key reason for using these tools are we've got very short simulation times, and which means you can iterate through many design concepts and various sort of parameters to find an optimized solution for our problem. So what this case study will demonstrate is how we can use Recordine and ParticleWorks to devise a cleaning system and simulate the cleaning system to clean off a mud occluded sensor, and also discuss how we can quickly and efficiently clean those sensors. So just to give you an insight into Recordine, Recordine's a multi-body dynamic software with the inclusion of flexible bodies. That's very useful for us engineers to help to design the correct actuators and define the correct loads to apply the motion that we require. It's good to understand both the motion but also the load transfer between different parts. And it's also very important to, with the inclusion of flexible body, it can help us to carry out some structural analysis and understand sort of strength results and fatigue results, and whether the system or the specific part is able to cope with the loads that we have defined. So what is multi-flexible body dynamics? Well, it's essentially the ability to include flexible bodies in a multi-body dynamic environment. And by dynamic, we mean a system where we have large translations and rotational displacements. So it's very important to have the capability to include flexible bodies in the system, so we can understand as a whole how the system will function and whether there are any specific limitations. So why Recordine? Well, Recordine's a powerful tool. It's able to model obviously rigid body systems with many parts, many contacts, and also able to include flexible bodies, and that this includes linear materials, non-linear materials, and also hyperelastic materials. It's also very robust, and it's used for a variety of applications. So it's not a one-trick pony, but can be used for gearboxes, vehicle suspension systems, and also even printing devices. And it's got a very intuitive GUI, a very modern GUI, which is very easy to use, very easy to view the model and to post-process the model. And as it's very intuitive, it's very easy to get to grips with it. So Recordine has a wide range of contact methodologies available. So it's able to conduct analytical contacts, which are based on primitive shapes, which are very efficient, but it's also able to use general contacts, which is essentially take any general surface, any surface from a CAD body, and able to define that as a contact surface. And essentially does this by discretizing the surface with a surface mesh and using that to define the contact boundary. Recordine also has various tools such as smoothing capabilities to provide a very accurate contact load, contact force. So it's got a very good contact technology, and one of the sort of plus points and benefits of it is it's very efficient. So it's able to include many contacts for a very small computational cost. And as mentioned, the USP of Recordine is its ability to include flexible bodies efficiently. Recordine does this by including a common solver for both the dynamics solving and also the flexible solving. There's two main methods that Recordine uses for flexible analysis, one being the RFlex method, which is a reduced flex method, and that's primarily used for sort of where we have fixed boundary conditions, fixed points of contact, and that uses a modal reduction system. So it's very efficient. But if we have a more complex problem, which requires whether it's moving boundaries, moving contacts, moving constraints, as we can see with this particular sheet example, then it's also able to do a co-simulation essentially between an FE analysis and a dynamic analysis. And as I mentioned, it's quite efficient because it's using a common solver to do so. Right, in this particular case study, we'll be making use of Recordine's capability to co-simulate with ParticleWorks. So there's a direct connection between them, and it's what we call a two-way coupling. So the fluid loads from the ParticleWorks model can be transmitted to the Recordine model, so we can see the effect it has on the various bodies. But likewise, the kinematic motion of the bodies can then be transferred back to the fluid, so we can see the effect from the bodies to the fluid. So this is what we call a two-way coupled simulation. And Recordine and ParticleWorks work well together, even in terms of solving. So Recordine runs on the CPU, whereas ParticleWorks is able to run on the GPU. So there's no compromise or clash between the two solvers in terms of resource allocation. So looking at the particular case, we're looking at a soiled LiDAR case. So what we've got here is a roof-mounted LiDAR with some particles, mud particles covering the lens. In this particular case, we've got about 40% of the lens covered in mud, and that's distributed across the lens surface. So this is quite a worst case scenario with quite a lot of coverage on the sensor. But this will be good to try and evaluate the various cleaning systems that we're going to look at. And one of the ways we'll be trying to clean it is using the wiping system. So this is a sketch or an image of the assembly. So we've got the roof of the vehicle, a rotating plate, which will be rotating these two wiper systems. We've got two wiper blades cleaning the lens. What we also have is the an actuator system, so it's actually spring actuated. So we've got a spring that pushes against the wiper blade holder, which in turn pushes the blade towards the lens. So this is the first step, which is to build the system first. So this is a fully rigid body simulation. We can see on the right the wiper blade, which is as mentioned, very rigid. So we saw no flexibility in that in the wiper blade. But this is an important step to evaluate if the multi-body dynamic system in the first case is modeled correctly. Here we can see the different effects of including and not including friction. So we can see on the left, without friction, we have only a normal component of the contact force there. But on the right hand side, we've got a diagonal force, which includes a tangential frictional force component. Now we can model or we can output this as a torque comparison. So this is measuring the driving torque by the rotating ring plate at the top of the roof, and we can see that with friction we get a much higher driving torque requirement. So the next step is to include some flexibility. As we know, a wiper blade is not going to clean or is not very efficient when it's rigid, so we need to include the flexible bodies. But instead of making the whole wiper blade flexible, we're able to pick sections of the wiper blade itself that are most likely to deform significantly. So in this case, we've taken this wiper blade model, we've sectioned it into 4 different parts. 2 of the parts will be rigid, 2 of the parts will be flexible, and the flexible parts are the blade tip and also the central section. And the reason for making those 2 parts flexible is, as I mentioned, they're the parts that will be deformed most significantly, while the other parts, which are more in a block structure, are likely to remain not as deformed as those ends. And the reason for doing this is to have an efficient simulation where we're able to run this design very quickly. Recordine is very clever in terms of connecting or separating the bodies, and one of the key features to make this possible is the ability to have force distributing rigid elements, and these are sort of rigid body elements or RBE elements if you've used finite element analysis, but they're essentially used to connect the surface of the flexible body to the rigid body. So here we can see a comparison of the rigid body on the left and the flexible body. So as you can see, the model on the right is functioning more like we'd expect, with the blade tip and the center of the wiper blade being able to deform. Okay, so the cleaning simulations that we're going to investigate are one using just spraying some washing fluid on the LiDAR with no wiping mechanism. The next phase is to use the wiping mechanism only, and then the third will be a mixture of the two, so using a wiper blade with washing fluid. So this is the model with only the spray jets. So we've got the soiled LiDAR, and either side we've got a jet on each side, so that's essentially a spray nozzle. In this particular model, we've kept the spray nozzles in the same place, but have a rotating lens. The reason being it's quite difficult to implement a system where we've got rotating jets. So this system makes use of having static jets and a rotating lens. So this is the output from the simulation. As you can see, we've got the interaction between the washer fluid and the mud. We can see the washer fluid able to displace the mud, but obviously what we can see towards the end is that it's not able to fully get rid of all the mud. The next simulation we're going to see is, as I mentioned, the wiping of the LiDAR. In this case, there's no cleaning fluid included. It's purely just trying to use the wiper blade, which will be rotating to clear the mud. And here you can see the simulation. So actually it's quite efficient in doing this. You can see the wiper blade being able to flex and also sort of collect the mud and then get rid of it on its final once it's being moved away from the lens. As you can see, there is some mud that remains on the sensor, but overall it's done quite a good job to clean the LiDAR. And this is the final setup where we've got a washer jet just to wet the surface and also the wiper blade as well. So what we can see is the water does help to try and displace some of the initial mud, but also wets the surface, so causes a slightly less or loosens up some of the mud. But overall has a very similar efficiency to what we had before with our wiper blade system. So it's not just pretty pictures, we've also got a graph to show to compare the three setups. So on the left we've got our mud occlusion, so that's how much the sensor is covered by mud. And over time we've got three different methods, and we can see with the blue line that the spray only method does not clean the sensor completely, so it's actually quite slow in its cleaning process, but towards the end still has around 10% of mud occlusion, whereas with the wiper only and wiper spray system we've got quite a very similar design, but we've got this steeper line which suggests a higher cleaning rate, which is quite important when we have, for instance, a sensor which is repeatedly being soiled. It's very important to make sure that it's being cleaned at a very high rate so that we're able to have the highest level of accuracy and visibility. Now in this particular case we've used a particular type of mud, and if you try to use something that's slightly thicker or stickier or even simulate dry mud, then we'll maybe able to see a difference between using the wiper only and wiper and spray, but that's a future simulation. Okay, so in summary we've seen how Recordine is able to, with its capability of including flexible bodies and in a multi-body dynamic environment, it's able to analyze complex systems using both rigid and flexible bodies. In this case, we've actually used the same parts split into sections of rigid and flexible bodies. And that's what we're able to do to create efficient models and provide very fast and accurate simulations. One section that we include is the ability to also co-simulate with control systems. Recordine has its own control system modeling tool called CoLink, but it can also interact with other systems modeling tools such as Simulink and MapleSim. It also has the capability to connect through an FMU. So what does the simulation allow us to do? So it would allow OEMs to determine an optimal configuration. So there's various parameters that we can change to get to an optimized solution for different conditions. And we're able to create an optimal configuration for passive active systems to help reduce sensor blindness. This optimization allows us to obviously make sure the sensors are operational at all times, improves obviously passenger safety, but also thinking about trying to increase the range of the vehicles. So it's important to make sure that these systems use the least amount of energy so we can maximize the utilizations of these vehicles. Okay, so I'll hand back to Karen, who will be will let us know if there's any questions.
Thank you very much, David, for that recap on particle works earlier, and Danajan for helping us understand how Recordine can be used with particle works to evaluate the efficiency of the cleaning process to reduce sensor blindness early in the design process. Okay, everyone, so this is your chance to ask any questions that you may have on what we've covered today as we move into Q&A. If you do have a question, please feel free to type that in the chat box that appears on your screen, and we'll endeavour to cover as many as we can. So we've had a couple of questions already about the recording. Now this will be available to you following today's webinar, so don't worry, you will get a copy. I think a few other questions have come through. So Danajan, can Recordine mesh the rigid bodies, or is it an external software that is required to do this?
Yeah, that's a good question. So Recordine has its own integrated comprehensive mesher, so you can take a working rigid body model, and mesh the parts of concern within the same graphical user interface without requiring a separate tool. And what's more, you can Recordine includes a feature called assist modeling. So if you've already got a rigid body model set up with all your contacts, loads, and constraints, you can preserve them within while meshing, so you don't have to mesh it and then have to reassign contacts, joints, and what other constraints you have. So that does save a lot of time in terms of amount of work to do to go from a rigid to a flexible body. And also Recordine does have the capability of running a modal analysis. There's a tool called the RFlex Gen tool, which is able to do that. So you can calculate the modes and carry out an efficient flexible body simulation using modal reduction method as described in the webinar.
I'm not sure who wants to take this one, but is it possible to model the effect of coatings on the LiDAR lens surface or the wiper blade, and how would this be done?
Yeah, so as demonstrated earlier, in Recordine you can model frictional forces between the wiper blade and the lens in this case. And you can modify some of the parameters, including contact stiffness, contact damping, but also those frictional parameters depending on the actual characteristics of the coating and how it interacts, whether that's the coating on the wiper blade or the lens. As for the fluid interaction, I'll probably hand over to David, who's got a bit more experience with that.
Yes, thank you very much. So within the fluid side of the simulation, in order to apply different coatings to the different surfaces, what we can do is we can create additional materials in our material property manager, and then from there we can apply different contact angles. So it's the contact angle which determines if something has a hydrophilic or a hydrophobic coating on it. So a very high contact angle, like 180, would be considered as hydrophobic, whereas a very low contact angle, so 0 to 10 degrees, would be hydrophilic. So we can change those contact angles within the material property manager to simulate different coatings applied to the different materials. In addition to that, we can also change what we call the interfacial surface tension between different fluids. So this would be changing the surface tension between the contaminant, so the mud in this case, and the cleaning solution. And this is the way that we would simulate something like a surfactant. So if we applied a soapy solution, which is going to behave differently to just a regular water solution. So yeah, that's how we would change the interaction and the different coatings applied within the fluid simulation.
So I think a few people want to know this. How long do the simulations typically take to run?
Yep, so I can take that question. The rigid body simulations only take a few seconds to run, so that's quite a good model to use when developing or creating the model. But when we add the flexibility, it takes around 1 to 2 hours, and that's expected with a significant number of degrees of freedom added with the mesh part. The fluid simulation depends on the number of particles. So if we're only simulating the mud, then the co-simulation is not significantly longer than just the flexible body simulation, because generally the fluid solution takes less time than it takes to solve the flexible body simulation. But when you're including the fluid spray, this does have some effect because you're adding quite a lot more particles. But as it runs on GPU, the fluid simulation runs on the GPU, and the flexible body simulation runs on the CPU. They don't affect each other in terms of resource. So it is quite efficient and only adds in the end a few tens of minutes to the overall simulation time.
Okay, I'm just a bit conscious on time. I think we will be able to cover this one. Would a GPU be required to run the particle simulation?
Yes, very good question. A GPU is recommended to run for the particle simulation. However, it's not entirely required. So for these very light simulations where we have just a few thousand particles suspended on the lens, and again, maybe a couple of tens of thousands of particles from the spray, these are so light that we could run on CPU. However, for the much larger simulations, such as the entire soiling simulation, the number of particles gets so large that while we can run on CPU, it becomes very time consuming and inefficient to run on CPU. So ParticleWorks is designed and been optimized to run on GPU, so it is far more efficient, both in terms of time and money, for the cost of the hardware and licenses to run on GPU. So yeah, our recommendation would be to have one of these high spec, or even just a gaming GPU. But if absolutely required, there are options to run on CPU instead.
Thank you very much for that, David. So unfortunately, there were a couple of questions that we didn't manage to get to, but either myself or my colleague will be in touch after today's webinar, so they will be answered. I want to take this opportunity to thank you all for joining us today. I hope you have found it useful and informative. If you are interested in a more detailed demonstration of ParticleWorks or Recordine, feel free to contact me if you haven't already done so. We'll be happy to discuss a time convenient for you and your team. Okay, so just before we go, thank you, Danajan, and thank you to David again. Okay, that's it, everyone. Thank you very much and enjoy the rest of your day.